This is a presentation of a comparative study of the SVM and KNN machine learning algorithms for the diagnosis of respiratory pathologies using pulmonary acoustic signals. Keywords used in this presentation like FCC, which stands for male frequency spectrum in sound processing. The male frequency spectrum is a representation of the short-term power spectrum of a sound based on a linear Gaussian transform of a log power spectrum on a nonlinear male scale of frequency. Another term is one-way ANOVA. Analysis of variance, is a collection of statistical models and their associated estimation procedures used to analyze the difference among group means in a sample. The background of the study is pulmonary acoustic parameters extracted from recorded respiratory sounds provide valuable information for the detection of respiratory pathologies. The automated analysis of pulmonary acoustic signals can serve as a differential diagnosis tool for medical professionals, a learning tool for medical students, and a self-management tool for patients. In this context, this study is intended to evaluate and compare the performance of the support vector machine and k-nearest neighbor KNN classifier in diagnosis respiratory pathologies using respiratory sound from RALE database, which is the database name. This is a related work on respiratory sound analysis. In the study conducted by Goldratt al., normal, wheeze and crackles respiratory sounds were classified using their power spectral density features. Electret microphones were used to record the respiratory sound from 129 subjects, and these were then classified using artificial neural networks (ANNs) and genetic algorithm GA-based ANNs. The classification accuracies found for ANN and GA-based ANN were 81 to 91% and 83 to 93% respectively. Methodology. The respiratory sounds used in this study were obtained from the RALE database, which is the only commercially available respiratory sound database and has been used by many researchers. The proposed system includes 4 processing stages, namely pre-processing, feature extraction, classification, and performance evaluation. In the feature extraction stage, the MFCC features are extracted from the respiratory sound signals, and these are fed to the SVM and KNN classifiers respectively in the classification stage. The SVM and KNN classifiers were used to distinguish normal airway obstruction and parenchymal pathologies. A block diagram of the proposed work is illustrated in figure 1. As you can see, the respiratory sound signal sampled at 10 kilohertz. That's the pre-processing, and that goes to the FCC features, and the MFCC features then is fed to the SPM classifier and KNN classifier respectively, and then the confusion matrix performance evaluation is done. Respiratory sound database. The respiratory sounds that were used in this work were obtained from the RALE database, which is the only commercially available respiratory sound database. These records were manually categorized into 3 different groups, namely normal, normal pathology, airway obstruction pathology, and parenchymal pathology. The figure 2 shows the respiratory sound signals associated with normal airway obstruction and parenchymal pathologies obtained from the Raleigh database. The figure 2 is showing the signal plot of respiratory sounds associated with normal and pathological conditions. The number 1, which is normal respiratory sound signal, is showing here with the time stamp, and the second diagram is showing the respiratory sound signal with airway obstruction pathology. As we can see visually, the difference is very showcased. And the third one is the respiratory sound signal with parenchymal pathology, which, as you can, the three are very different on just visually observing. Respiratory sound pre-processing. Respiratory sound signals are subject to noise, such as heart sounds and other artifacts. The Raleigh database comprises recordings that have been filtered to remove the heart sound and artifacts. Parametric representation. The spectral characteristics of the pulmonary acoustic signals are vital in determining the respiratory pathology. One of the parametric representation which depicts the spectral characteristics of signals is male frequency spectral coefficients MFCC. MFCC are associated with a highly effective feature extraction algorithm used in speech signal processing. Furthermore, some researchers have previously implemented MFCC for respiratory sound analysis and have obtained promising outcomes. Statistical test. In this study, analysis of variance ANOVA was used to test the significance of the feature vector. One-way ANOVA is used to test the null hypothesis of samples with more than two groups. More specifically, one-way ANOVA is used to test the equality of three or more means at one time using variances. Classifications. In this work, two different classifiers were used, namely support vector machine SVM and k-nearest neighbor KNN. A detailed description of the classifiers used can be found in the following section that we are going to discuss now. Support vector machine SVM. The SVM classifier is a kernel-based supervised learning algorithm that classifies the data into two or more classes. SVM is particularly designed for binary classification. During the training phase, SVM builds a model, maps the decision boundary for each class, and specifies the hyperplane that separates the different classes. Increasing the distance between the classes by increasing the hyperplane margin helps increase the classification accuracy. SVM can be used to effectively perform nonlinear classification. Detailed information on the SVM classifier will be discussing later on. In this study, the MFCC features vector was fed to the SVM classifier to distinguish normal airway obstruction and parenchymal pathological conditions. As mentioned earlier, the SVM classifier is a kernel-based classifier. Kernel function is a mapping procedure done to the training set to improve the resemblance to the linearly separable dataset. The purpose of the mapping is to increase the dimensionality of the dataset and is done efficiently using a kernel function. Let's talk about the k-nearest KNN. In pattern recognition, the KNN algorithm is instant-based learning method used to classify objects based on their closest training examples in feature space. An object is classified by a majority vote of its neighbors, that is, the object is assigned to the class that is most common amongst its k nearest neighbors, where k is a positive integer. In the KNN algorithm, the classification of a new test feature vector is determined by the classes of its k nearest neighbors. Here, the KNN algorithm was implemented using Euclidean distance metric to locate the nearest neighbor. The Euclidean and distance metric, which is d in bracket x comma y between 2 points x and y, is calculated using the equation where n is the number of features such as that x equals to curly bracket open x1 x2 x3 and other xn, and y equals to curly bracket open y1 y2 y3 and so on. The number of neighbors, that is k, used to classify the newest vector was varied in the range of 1 to 10, and its effects on the classification performance were determined in the form of classification accuracy with standard deviation. Now we'll talk about the results and discussions which is used by the SPM and KNN. The extractor features were tested using one-way ANOVA, and the features were found to be significantly different between the groups. The FCC features were separately binary normalized and bipolar normalized. Normalization is done to standardize the range of independent variables. Let's see the training data now. The training was conducted using 9 sets, and the remaining set was used for testing. This method was repeated 10 times, and the average mean classification accuracy is reported. The performance outcome of the SPM and the KNN classifier for binary normalization features are reported in Table 1 and Table 2 respectively. The performance outcome of the SPM and the KNN classifier for bipolar normalized features are reported in Table 3 and Table 4 respectively. In the Table 1, the average deviation of the classification accuracy are tabulated. The standard deviation of the classification clearly reveals the consistency of the classifier results. If the standard deviation is higher, the classification results are considered inconsistent, and this inconsistency also depends on the parameters of the classifier. As we can see in the Table 1, which is showing the performance outcome of the SPM classifier for binary normalized data, the SPM classifier with the RVF kernel obtained the maximum classification accuracy of 89.54% with a standard deviation of 0.39 for the binary normalized data with the conventional validation method. Let's go to the Table 2, which is showing the performance outcome of the KNN classifier for binary normalized data, where the KNN classifier with a k value of 2 gave the maximum classification accuracy of 94.81%, which is this one, 94.81% with a standard deviation of 0.42 for the binary normalized data with the conventional method. Table 3 shows that the SPM, let's see the Table 3, which is right here, which shows the performance outcomes of the SPM classifier for bipolar normalized data. Here we can see the classification accuracy is 92.119%, and the standard deviation is 1.58, which is using the linear RVF tenfold cross validation. Now we're gonna look at the table 4, which is showing the performance outcome of the KNN classifier for bipolar normalized data. As we can see, in the K value is 1, the conventional validation is 97.53%, and the standard deviation is 0.29%, and we can see the value increase for 2, 3, 4, 5, 6, 7, 8, 9 till 10, and as the K value increases, increment is swing from 1 to 10 with the classification accuracy percentage as well. Now if we see the tenfold cross validation, we have this here. We have the classification accuracy is 98.26%, and the standard deviation is 0.32%. Now we go for the table 6, which is showing the confusion matrix for the KNN classifier. Here the K value 1 normalization bipolar is the best result showcased. Increasing the K value increases the number of neighbors, which may lead to a decrease in performance, as we see showcased here in the table 4. As we have seen, as the neighbor increases, the number of neighbors, which may lead to a decrease in performance, because the chances of including a data point from a different class becomes higher with the increase of nearest neighbors, which can be showcased here, where you can see the percentage for the K value 10 has 95.14% with the standard deviation of 1.669, where for the value 1 is the 97.53% with the standard deviation 0.29, and as the neighbor increased, the accuracy decreased. Now we'll talk about the limitation with this study. The limitation of this study is the number of data used. The number of data used in this study is very low, and the data collection was carried out in a controlled environment. The analysis of data with respect to clinical settings should be carried out in future with a larger database. The analysis can be further extended to other feature extraction techniques and machine learning algorithms. Those were the limitations. And we'll talk about the results. The pulmonary acoustic signals used in this study were obtained from the Rayleigh Lung Sound database. The pulmonary acoustic signals were manually categorized into 3 different groups, namely normal, airway obstruction pathology, and parenchymal pathology. The male frequency spectral coefficient EMFCC features were extracted from the pre-processed pulmonary acoustic signals. The EMFCC features were analyzed by one-way ANOVA and then fed separately into the SVM and KNN classifiers. The performance of the classifiers were analyzed using the confusion matrix technique. The statistical analysis of the EMFCC features using one-way ANOVA showed that the extracted EMFCC features are significantly different. The classification accuracy of the SVM and the KNN classifier were found to be 92.19% and 98.26% respectively, where 92.19% can be seen in the SVM, and in the KNN classifier with a higher percentage of 98.26% is showcased. The conclusion of the study: although the data used to train and test the classifiers are limited, and the classification accuracy found are very satisfactory. The KNN classifier were better than the SPM classifier for the discrimination of pulmonary acoustic signals from pathological and normal subjects obtained from the Raleigh database.